Hi, I hope you are doing well. Today, as usual, you will join Cosmos with the usual intimacy. Today we are posting two videos. As usual, in addition to our video, this video is brought as a special video. This video is being posted at the request of a viewer on our YouTube channel. His name is Joe Degelman. Today we are talking about the constancy of the speed of light in GPS. We hope to reveal many very important and wonderful facts about the constancy of the speed of light in GPS in this video. We invite you to stay with Cosmos until the last few seconds of this special video. The Global Positioning System, GPS, represents one of humanity's most remarkable technological achievements, combining sophisticated satellite technology with intricate physics principles to deliver precise positioning worldwide. At the heart of GPS functionality lies a fascinating question about one of physics' most fundamental constants: the speed of light. This report explores the complex interplay between theoretical physics, relativistic effects, and practical engineering solutions that address the constancy of light speed in GPS operations. The analysis reveals that while the speed of light maintains constancy in certain reference frames relevant to GPS, its behavior becomes more nuanced when considering the rotating Earth, requiring sophisticated corrections to maintain the system's extraordinary precision. Einstein's special theory of relativity rests on the principle that light travels at a constant speed in vacuum, approximately 299,792,458 meters per second, regardless of the motion of the light source or observer. This postulate has profound implications for our understanding of space, time, and the fundamental nature of the universe. In the context of GPS, this principle takes on immense practical significance since the entire system relies on precisely measuring the time taken for electromagnetic signals to travel between satellites and receivers on Earth. The constancy of light speed forms the foundation of the range measurement equation used in GPS positioning. This equation relates the distance between a satellite and receiver to the time taken for the signal to travel between them, multiplied by the speed of light. Any variation or uncertainty in the speed of light would directly translate to inaccuracies in position calculations. However, the seemingly straightforward principle of light speed, constancy, becomes considerably more complex when applied to the real-world scenario of GPS operation involving rotating reference frames and relativistic effects. The practical implementation of GPS must address a fundamental question: does light truly travel at the same speed in all directions and reference frames relevant to the system? The answer, as we will explore, involves sophisticated physics concepts including reference frames, relativistic effects, and transformations that challenge our intuitive understanding of space and time. An important distinction must be made between one-way and two-way measurements of light speed. While two-way light speed invariance has been extensively verified through experiments, direct one-way measurements are considerably more challenging. This distinction becomes particularly relevant for GPS, which inherently involves one-way transmission of signals from satellites to receivers. Many experiments claiming to confirm light speed constancy have been conducted in the non-inertial frame of the rotating Earth, despite the principle being formally applicable to inertial frames. This creates theoretical challenges that must be carefully addressed in the design and operation of the GPS system. To properly analyze light speed behavior in GPS, we must first understand the reference frames used in the system. Two primary reference frames are crucial for GPS operations: the Earth-Centered Inertial (ECI) frame and the Earth-Centered Earth-Fixed (ECEF) frame. The ECI frame has its origin at Earth's center, but does not rotate with the planet. Instead, it maintains a fixed orientation relative to distant stars, making it effectively an inertial frame for the purposes of GPS calculations. According to the GPS Interface Specification, IS-ICD 200, GPS signals propagate in straight lines at the constant speed c in this ECI frame. This assumption of light speed isotropy, equal in all directions, in the ECI frame has been rigorously tested. Research by Wolf and Petit established a limit of dc to c 5 pi 10 9 for potential variations in light speed within this frame, confirming a high degree of isotropy. This experimental validation provides strong support for the constancy of light speed in the ECI frame, underpinning the fundamental equations used for GPS positioning. The ECEF frame also has its origin at Earth's center, but rotates with the planet. In this frame, points on Earth's surface have fixed coordinates, which is advantageous for describing receiver positions. However, the non-inertial nature of this rotating frame introduces significant complications for light propagation analysis. The transformation between these reference frames represents a critical aspect of GPS calculations. The GPS equations employ a Galilean transformation between the ECI and ECEF frames, which is non-relativistic in nature. This transformation choice has profound implications for light speed behavior within the system. To address these relativistic effects, GPS employs a sophisticated two-step correction procedure. Each satellite clock signal is offset by a relative frequency adjustment of approximately 0.0445 through frequency mixing. This adjustment approximately corrects for the combined relativistic effects. Residual corrections are implemented in software within each GPS receiver, based on correction parameters broadcast by the satellites. These parameters are updated daily from ground stations. This correction process has been experimentally validated. A time transfer experiment using GPS satellites tested the standard Sagnac correction and verified the validity of these corrections to within approximately 5 nanoseconds. This empirical validation supports the theoretical framework underlying GPS operations. Several other relativistic effects become relevant at extremely high precision levels, approximately 1 centimeter in position or less than 0.03 nanoseconds in time transfer accuracy. These include relativistic corrections to satellite orbits, Shapiro time delay, a general relativistic effect on signal propagation, and the lens-thirring effect, frame dragging due to Earth's rotation. However, various non-relativistic effects often have greater practical impact on GPS accuracy. These include ionospheric time delays, partially addressed through a two-frequency technique, tropospheric propagation effects, clock drifts, and unmodeled forces affecting satellite orbits. Among these, tropospheric effects are considered particularly challenging, potentially causing errors of approximately 1 nanosecond. The mathematical description of light propagation in GPS provides a rigorous framework for understanding the constancy of light speed across different reference frames. The GPS range measurement equation forms the foundation of this mathematical framework. The fundamental equation governing GPS positioning is RTR, RSTs, CTR, TS. This equation relates the positions of satellites and receivers to the time taken for signals to travel between them, assuming constant light speed c in the ECI frame. This equation has been rigorously tested and verified, providing strong empirical support for light speed constancy in the inertial frame. The transformation between the ECI and ECEF frames introduces mathematical complexities. The Galilean transformation used in GPS calculations, while non-relativistic, serves as a practical approximation. Under this transformation, the speed of light becomes direction-dependent in the ECF frame, even while remaining isotropic in the ECI frame. A more rigorous approach would involve fully relativistic coordinate transformations. Research indicates that the Galilean transformation represents a first-order approximation to the relativistic transformation, explaining why GPS positioning has worked remarkably well despite using this simplified approach. The Sagnac effect can be mathematically formulated by calculating the difference in travel times for signals propagating in different directions relative to Earth's rotation. This difference must be accounted for in GPS calculations to achieve accurate positioning. The mathematical framework for the Sagnac effect further demonstrates the anisotropy of light speed in rotating reference frames. Experimental evidence plays a crucial role in assessing light speed constancy across different reference frames relevant to GPS. Several key experiments and measurements provide valuable insights into this complex phenomenon. Wolf and Pettit conducted rigorous tests of light speed isotropy in the ECI frame, establishing a limit of DC 5/10⁹ for potential variations. This high degree of isotropy supports the assumption of constant light speed in the inertial frame, validating a fundamental premise of GPS operations. The GPS system itself serves as a sophisticated experimental platform for investigating lightspeed behavior. The range measurement equation has been extensively tested and verified, providing empirical validation for the theoretical frameworks underlying GPS operations. Experiments involving the Sagnac effect on rotating platforms demonstrate measurable anisotropy in light speed. These observations align with theoretical predictions and have direct implications for GPS operations, particularly for signals traveling in east-west directions across Earth's surface. The measurement of one-way light speed presents significant experimental challenges. Historical difficulties in detecting light speed anisotropy stemmed partly from the lack of direct one-way measurement capabilities relative to moving observers. The GPS system provides unique opportunities for such measurements, as it allows precise timing of signals traveling one way from satellites to receivers. The effectiveness of relativistic corrections applied in GPS operations provides indirect experimental evidence supporting the theoretical framework. A time transfer experiment using GPS satellites verified the standard Sagnac correction to within approximately 5 nanoseconds, confirming the accuracy of the corrections implemented in the system. The practical implementation of GPS navigates the complex theoretical landscape of light speed behavior through sophisticated engineering solutions. These implementations must balance theoretical rigor with practical considerations to deliver highly accurate positioning services. To address relativistic effects, GPS satellites' clock frequencies are adjusted by approximately 4.45 kHz-10 through frequency mixing. This adjustment approximately corrects for the combined relativistic effects, including time dilation, gravitational frequency shift, and the Sagnac effect. Residual corrections are implemented in software within GPS receivers based on parameters broadcast by each satellite. These correction parameters are updated daily, ensuring continued accuracy despite changing conditions. While relativistic effects represent significant challenges, various non-relativistic effects also impact GPS accuracy. Ionospheric time delays are partially addressed through a two-frequency technique that allows these delays to be approximately canceled out. Tropospheric propagation effects, clock drifts, and unmodeled forces affecting satellite orbits represent additional challenges that must be addressed through sophisticated algorithms and regular system updates. The practical implementation of GPS represents a remarkable balance between theoretical complexity and practical engineering requirements. While a fully relativistic approach might seem theoretically preferable, the Galilean transformation used in GPS calculations serves as an effective approximation that delivers excellent results while simplifying implementation. The success of GPS demonstrates that practical systems can navigate theoretical complexities through careful design and appropriate approximations, delivering extraordinary performance despite the subtle physics involved. The analysis of light speed constancy in GPS has profound implications for our understanding of fundamental physics, particularly regarding the application of relativity principles in practical contexts. The successful operation of GPS, incorporating corrections for relativistic effects, provides strong validation for Einstein's theories of special and general relativity. The system's remarkable accuracy confirms that relativistic effects occur precisely as predicted by theory, requiring explicit corrections to achieve accurate positioning. The analysis reveals important nuances in the principle of light speed constancy. While light speed remains constant in inertial frames, such as the ECI frame, it becomes anisotropic in rotating frames, such as the ECF frame. This distinction highlights the importance of specifying reference frames when discussing light speed constancy. The distinction between one-way and two-way measurements of light speed emerges as particularly significant. While two-way light speed invariance has been conclusively verified, one-way light speed constancy presents more complex theoretical and experimental challenges. GPS provides unique opportunities for investigating one-way light speed behavior through precise timing of satellite signals. Traditional interpretations treat the Sagnac effect as a time correction in GPS operations. However, deeper analysis suggests a reinterpretation based on fundamental light speed anisotropy in rotating reference frames. This perspective emphasizes the Sagnac effect as direct evidence of light speed anisotropy rather than merely a correction factor in calculations. The study of light speed constancy in GPS continues to evolve, with several promising directions for future research and development. Future research could develop more sophisticated theoretical frameworks for analyzing light propagation in rotating frames. While the Galilean transformation currently used in GPS provides excellent results as a first-order approximation, more rigorous relativistic transformations might offer insights for next-generation systems requiring even greater precision. The theoretical possibility of making light speed appear isotropic in the ECEF frame through standard synchronization presents intriguing possibilities despite practical limitations. Future research might explore modified synchronization schemes that maintain advantages while addressing current limitations. As GPS technology advances, opportunities emerge for more sophisticated experimental protocols measuring one-way light speed. These measurements could provide deeper insights into fundamental physics while potentially improving system accuracy. Emerging quantum technologies might offer new approaches for timing and synchronization in future navigation systems. Quantum entanglement and other quantum phenomena could potentially enable novel methods for addressing the challenges associated with light speed behavior in different reference frames. The constancy of the speed of light in GPS represents a fascinating intersection of theoretical physics and practical engineering. This comprehensive analysis reveals a nuanced picture. While light speed remains constant and isotropic in the Earth-centered inertial frame, it becomes anisotropic in the Earth-centered Earth-fixed frame that rotates with our planet. This anisotropy, evidenced by the Sagnac effect, requires sophisticated corrections to maintain GPS accuracy. The GPS system successfully navigates these theoretical complexities through a two-step correction procedure that addresses relativistic effects, including time dilation, gravitational frequency shift, and the Sagnac effect. These corrections, combined with the practical approximation of using a Galilean transformation between reference frames, enable GPS to achieve remarkable accuracy despite the subtle physics involved. The analysis of light speed constancy in GPS has significant implications for our understanding of fundamental physics. It confirms key principles of Einstein's relativity theories, while highlighting important nuances in their application to rotating reference frames. The distinction between one-way and two-way measurements of light speed emerges as particularly significant, with GPS providing unique opportunities for investigating one-way light speed behavior. As GPS technology continues to advance, opportunities emerge for deeper investigations into light speed behavior and more sophisticated correction methods. These developments promise to enhance both our theoretical understanding of fundamental physics and the practical performance of global navigation systems, demonstrating the profound connection between abstract physical principles and transformative technologies. If you haven't subscribed to us yet, please subscribe. If you like the video, please give it a like. Don't forget to share this video with others. We'll see you again tomorrow with a video like this. Until then, stay tuned with Cosmos. Have a nice day. Bye.